All right, here we go. Another example. Find the intervals on which f is increasing and the intervals on which f is decreasing for this function f of x equal to 2x squared over x squared minus 1. So we have this rational function now. So it's division. We might have some division by 0. That's something we're going to have to keep in mind. But let's start the process here. First step, we want to figure out the intervals of increase, decrease. Let's get the derivative. We got to calculate the derivative. So that's step 1. All right, so when we do this, let's look at what we have here. It's a fraction. There's variables on the top. There's variables on the bottom. We got to use quotient rule. So let's write down our fraction as a product. So top function times the bottom function. And then we'll do 2 copies of that. Top function times the bottom function. In the first copy, we apply the derivative to the first part. In the second copy, we apply it to the second part. Then we put a minus sign in between. And then this is all over the original denominator, all squared. All right, so that's quotient rule. Then we keep differentiating. So let's get this. This is 4x, and then this is a 2x over here. So let's keep going. We get 4x times x squared minus 1 minus 2x squared times 2x all over x squared minus 1 squared. Don't do anything to the denominator. So we don't normally multiply this out or anything. So it's better to leave it like this, actually. But we do want to try to simplify the numerator. So when we have quotient rule, or when we have a fraction, a lot of our work in terms of simplifying happens in the numerator. So let's multiply this out, and we get 4x cubed minus 4x, and then what do we get over here? Minus 4x cubed. Oh, nice. Simplifies kind of nicely. So the 4x cubes are going to cancel. And what we're left with then for our derivative is negative 4x over x squared minus 1 squared. All right, so that's our derivative. It's about as simple as we can get it. So now the next step is we want to look at where the derivative is 0 and where the derivative is undefined. And for a fraction, this comes down. The only way a fraction can be equal to 0 is if the numerator is 0. And for a fraction to be undefined, when it's a rational function like this, it's polynomial divided by a polynomial, the way it can be undefined is if the denominator is equal to 0. So that's kind of why quotient rule is helpful here. There's other ways to differentiate this, but quotient rule kind of gives us the fraction, and it gives it to us in a format that's going to be easier to work with. So again, there's other ways to differentiate this, but quotient rule does a pretty nice job in giving us something that's usable, or almost immediately usable. All right, so let's take our numerator, and we're going to set that equal to 0. So negative 4x equal to 0. And then solving that for x, we get x is 0. And then for our denominator, we're going to set our denominator equal to 0. So x squared minus 1 squared is equal to 0. And well, we got to solve this. And the only way you can square something and get 0 is if it was 0 to begin with. So the term inside the parentheses here, x squared minus 1, has to be equal to 0. Another way to see that, just apply the square root to both sides. Square root cancels the squared, and then square root of 0 is 0. Okay, so x squared minus 1 could be 0. And then let's keep going. Let's keep solving this here. You could factor this. So this factors into x minus 1 times x plus 1, if you want to think of it like that. Or another way is you could add 1 to both sides. And then you would get, and then do the square root. And whenever we apply the square root to both sides of an equation, and I really probably should have done it over here, but I knew I was going to get 0. But whenever we apply the square root, plus or minus goes in front. So x equal to plus or minus 1. So whenever we actually apply, while we're solving for x, whenever we apply the square root function in our kind of solution method, plus or minus. So x squared equal to 1, we should get 2 solutions, x equal to plus or minus 1. You also see that if you factor. So if we factored into x minus 1 times x plus 1, you'd get the same solutions. So there's different ways to think of how to solve this. In this case, though, we get x equal to plus or minus 1. And all right. So what did we find? Well, we found x could be 0, and we found that x is 1 and x is negative 1. Now, these are all 3 important values for finding the intervals of increase-decrease. Let's just make a note, though. Only one of these is technically a critical number, and that's x equals 0. So this is a critical number because it's in the domain of f. So you can plug 0 into our original function, and you get 0 divided by negative 1, perfectly good number. Now, these other ones, these 1 and negative 1, they're still important for finding the intervals, but these are not technically critical numbers because when we plug 1 into this function, we get 2 divided by 0, undefined. Or if I were going to plug negative 1 in, I'd get, again, 2 divided by 0, again undefined. So these, maybe call these non-critical numbers. They're still important for our purposes, but they're just not in the domain of our function. So we just want to make kind of a slight distinction here between these. All right. So the hard work is done. Finding the derivative, simplifying the derivative, and then solving these equations. Now we need to set up our sign chart. So let's do our sign chart. Step 3, we're going to do our sign chart for f prime. So this means we're going to draw our number line. And it's a rational function. So that means the domain is almost all real numbers except where the denominator is equal to 0. So it's this entire number line. And then let's just plot those x values that we found from before. So we found what? X equals 0, x equals negative 1, and x equal to positive 1. And when we do this, just to kind of keep track, just as like a bookkeeping type thing, let's use a filled in dot for x equals 0 because that was a critical number. And then let's use an open circle at negative 1 and positive 1 because those weren't critical numbers. They're still important, but they're not technically critical numbers. We'll see why that distinction is important in a later lesson. But right now, let's just keep track of that. And so what these 3 x values do is they split up our number line into intervals. So we're going to have this interval from minus infinity to negative 1. We'll have the interval from minus 1 to 0. we'll have the interval from 0 to 1, and then we'll have the interval from 1 to infinity. And what we're going to do is we're going to check the sign of f prime on each of those intervals. And so the way we do that is we look at our derivative, and we found it before. It was negative 4x over this x squared minus 1 squared. And we really just consider the different factors here. So we have a negative 4x, that's one factor. And then the other factor here is this x squared minus 1 squared. And then we're going to use those two factors to see what the sign is for f prime. All right. So let's start with this interval from minus infinity to negative 1. We want to pick a test number somewhere in that interval. So something less than negative 1, make it easy. Let's do negative 2. And when I plug negative 2 into this first factor, the negative 4x, I get positive 8. I don't really care about the number, I just care about the sign, so it's positive. Now when we go to this second factor here, you can try it out. When I square negative 2, I get positive 4, so I get 3. And then when I square 3, I get a positive number. Now, the nice thing about having something squared is whenever we square a number, whether it's positive or negative, if we square a positive number, the result is positive. If we square a negative number, the result is still positive. So when you see this squared, makes things really simple for us because we can just go right across the row and say, well, everything's positive. That factor is always going to be positive. So that's kind of nice. All right. So now we just need to test this negative 4x factor. So let's go to the interval from negative 1 to 0. Pick a test number that's somewhere in there and easy to work with. So maybe like negative 1/2. Take the negative 1/2, multiply it with the negative 4x. We get positive 2. Again, we don't really care about the number, just the sign. So it's positive. Then we go to the next interval. Again, make it easy to work with. So 1/2 would work. 1/2 times negative 4x is going to be negative 2. So that's negative. So we record that there. And then we go to the last interval, pick a number. So maybe t equal to positive 2. If you want to just indicate where your test numbers are, that's fine. Let's take 2, plug it into this factor. We get negative 8. Again, we're just interested in the sign, so it's a negative. All right, so we've gone through all of our factors for our fraction here. And so for this first interval, we want to figure out, well, what's the sign of f prime? Well, we have a positive number divided by a positive number. The result is going to be positive. Then over here, we have a positive number divided by a positive number. The interval f prime is going to be positive. Then we have a negative divided by a positive, so the result is negative. And then a negative divided by a positive, so negative. So that's us filling in our sign chart using test numbers. All right, not too bad. Now, the last thing we need to do is just, figure out what f is doing. So all of this discussion has been about f prime, but we're actually interested in function f. We want to know what function f is doing. Is it increasing or decreasing? And so when f prime is positive, that means f is increasing. And when f prime is negative, that means f, our original function, is decreasing. So we just go through and indicate, make that determination, and put it in our sign chart. And now we just need to kind of state our result. And so what we found is that our function was increasing on the interval from minus infinity to minus 1, and on the interval from -1 to 0. Now, why it was kind of helpful to keep track, -1 is not in the domain of our function. So we can't actually combine these intervals into just one interval. So even though this one ends at -1 and this one starts at -1, because our function is undefined at -1, we can't stitch these together. So it's not increasing on that entire interval. It's increasing on this one, and it's increasing on this one, kind of separately. Same thing for the decreasing. So we see that it's decreasing on the interval from 0 to 1. And then it's also decreasing on that interval from 1 to infinity. But because we have this point there in the middle where our function's undefined, we can't stitch these two intervals together. So we have, this interval ends at 1 and this one starts at 1. But unfortunately, because our original function is undefined at 1, we can't combine these intervals into one kind of larger interval. And so if you were to graph this function out, what you'd actually see is there's a jump. There's an infinite jump at -1 and +1. And so the graph is increasing on one side and it's increasing on the other, but going from the left interval here to the right interval there's going to be a big jump. So you're actually going to almost decrease going from one interval to the other. And that's because there's a vertical asymptote. So, try graphing this function just to see what's going on. But for the purposes of finding the intervals of increase-decrease, we're just noting here that because our function is undefined at -1 and +1, we can't actually combine these intervals. All right, so there we go. We have our answer. We know the intervals where our function's increasing, decreasing, and what we used with a little bit of work is that first derivative. We calculated our first derivative, we simplified it, then we figured out where our derivative was 0, where our derivative was undefined, and then that kind of split up our number line. Since we found 3 x values, that split it up into 4 separate intervals. And then we used test numbers to figure out the sign of f prime on each of those 4 intervals. And that told us then what f was doing. So when f prime is positive, f is increasing. When f prime is negative, f is decreasing. All right, so these are, they're pretty fun. I like doing these. And what we're going to do is in the next lesson, we're going to do this all over again, but for the second derivative. And we're going to see what the second derivative tells us about our original function. So this strategy of using sign charts and figuring out where the derivative is 0 and undefined, we're going to do this all over again, but now for the second derivative. So we'll see you then. Bye-bye.